Hello everyone. So in this lecture we're gonna have a review of what voltmeters and ammeters are and how we can model those properly in a circuit, or how to connect them properly in a circuit to be able to measure these values, or once we have them connected, how can we take them into account in terms of what kind of effect they would have on the circuit. So we're going to discuss that on a simple circuit so that you can relate the concept into an actual measurement. So let's assume that we have two resistors in series to each other, and then we apply a source. This is a very simple circuit. We have analyzed this circuit before, and you should be quite familiar with the current that is passing through and the voltages in the circuit. So quickly, if this is ground, I'm not going to go through that process. You can see that from other lectures so far. The current that is going to pass through, I'm going to call that IS, would be equal to voltage divided by the two resistors added to each other, and then obviously the voltage of this node would be Vs with respect to the ground, assumed to be the lower potential, and the voltage in the middle, I'm going to call that V1, is simply calculated as a voltage divider. So that would be R2 over R1 plus R2 times the total voltage across, which is Vs. Okay, so now let's say I want to measure this current or this voltage in the circuit. So the equipment that we have for that are called voltmeters and ammeters. For the voltage, a voltage or any voltage is measured across two terminals, and a current is measured through two terminals. And you have to be mindful of how to use these terms properly. So when you measure a voltage, the voltage is across two terminal, but then when you're measuring a current, usually you have to open up the path through which the current was originally going through, and then from the two connections that is a result of opening up your circuit, put your ammeter in and measure the current that is going through those two terminals. So let's start with a voltmeter, and let's assume the voltage that I'm trying to calculate is this voltage. I'm going to use this symbol for my voltmeter and connect it to the two terminals across R2, at which point, assuming that this is the lower terminal of the voltmeter, and the negative terminal of the voltmeter, and this is the positive terminal of the voltmeter, the voltage that I would calculate would be V1, the voltage that I would measure would be V1 minus 0, or in other words, the V1 that we see here. Okay, so now what is this voltmeter? In other words, how does the measurement happening? Now, the new voltmeters are all digital voltmeters. And what's going on inside is that the signal comes in, gets conditioned, then it's applied to a to D device, which stands for analog to digital converter. And basically that voltage turns into a digital number. The digital number then is read into a microprocessor and gets processed and displayed on a display. How exactly this conversion happens, how our microcontrollers interpret those voltages, how does the A to D operate, all of those are really good questions, and I really encourage you to start looking into answers to those kind of questions. We may end up discussing those way after, like many lectures beyond what we're discussing at this point, because for understanding of those topics you have to have an advanced knowledge of microelectronic devices, which at this point in terms of a sequence of the material we haven't discussed yet. But eventually I hope that we get to discuss those in other courses that comes after this course, which is Circuit 1. Now, that aside, the other question is that now that I'm using a voltmeter, would this voltmeter have an effect on the circuit that I am measuring? And the answer, intuitively speaking, should be yes, because before the measurement, obviously these two terminals were only connected basically in this terminal of the R resistor 2 was only connected to terminal of the resistor 1, and the other terminal only directly connected to the bottom terminal of the source, whereas now you have these two extra connections, and these extra connections, unless internal to this, they're just open circuit and not connected to anything. Making those connections is going to change the circuit, right? In other words, by trying to measure the voltage of the resistor, most likely you're actually changing the voltage of that circuit, which you can agree with me that that's not really what you expect. In other words, you want to measure the voltage of the circuit that only has R1 and R2 in it, not a circuit that includes a voltmeter also connected to it. So ideally speaking, you want the voltmeter to be an open circuit. In other words, you want to make sure that by connecting the voltmeter, you're not drawing any current into the device, so that by that you're changing the currents in the circuit and changing the voltages of the circuit. So ideal voltmeter is an open circuit. That's what you want. If the voltmeter is an open circuit, you can basically simply assume that this is not connected to anything, which you're back to your original circuit, and the voltmeter is not going to have any effect on your measurement. In reality, that's not the case. The voltmeter actually is not an open circuit. There is a circuitry inside. You can model that circuitry with a simple resistance. In other words, you can look into that voltmeter, calculate the equivalent resistance that you see looking into those two terminals, and replace the voltmeter with an equivalent resistance. So let's do that. Let's imagine that I know what the equivalent resistance of the voltmeter is. So I'll remove that with an equivalent resistance, and I'm going to call that R voltmeter. Okay? So originally the voltage of the circuit was V1, which was R2 over R1 plus R2 times Vs. Let's now calculate the voltage of the circuit. Okay, so to do that, again, we can resort back to basics. And let's define our nodes, define currents, I1, I2, I'm going to call that IV. You can pick any name that you want. And done. Next, we write KCL. So KCL, you can write KCL for 3 nodes. That one you don't have to write a KCL for. I'm going to write it for that node and that node. Obviously, these two are equal to each other, and I could have actually picked the same current to begin with, but let's just stick to what we have there. So IS is equal to I1, and for that node, I1 is equal to I2 plus IV. Then I move on to equations for component. This voltage up here is Vs. Again, I'm writing the equation for this component when I'm labeling that, so I don't have to write the equation for this component. Now, for R1, equations for components, I1 is equal to Vs minus V1 divided by R1. I2 is equal to V1 minus 0 divided by R2. And IV is equal to V1 minus 0 divided by RV. With all that, I can now take the equations for the currents, put them up here. So I1, which is Vs minus V1 divided by R1, Vs minus V1 divided by R1 is equal to I2, which is V1 divided by R2 plus IV, which is V1 divided by RV. So I move these around, so Vs divided by R1 would be V1 times 1 over R1 plus 1 over R2 plus 1 over RV. So V1 would be Vs over R1 times 1 over R1 plus 1 over R2 plus 1 over RV inverse. So if you simplify that, you would realize that that's equal to R2 in parallel with RV over R1 plus R2 in parallel with RV. It's just, you have to do the calculation. Now, how did I know that? I actually used the trick or used a shortcut. So this is obviously always the process to do the calculation, but I can look at this and say, okay, these two resistors are in parallel to each other. Once I put them in parallel, the result of these two in parallel to each other is in series with R1, and the voltage in the middle would be a simple voltage divider. Sorry, S is time Vs. So it would be R2 in parallel with RV over R2 in parallel with RV plus R1 times the total voltage across. So look at this. Before I put the voltmeter in, this was the voltage. Now after I put the voltmeter in, this is the voltage. And obviously you can see the difference, right? Now with this, you should get a better feeling for why the ideal voltmeter should be an open circuit. Look at this. If the voltmeter is an open circuit, then this is infinity, right? And this is infinity. So R2 in parallel with infinity is R2. R2 is in parallel infinity with R2. So this is going to go back to R2 over R1 plus R2, which is what you expect. You could intuitively say that too, because if that's an open circuit, it's gone and it goes back to what it was before. So there you go. Now, since it's not infinity, you can actually calculate the error. If you know what your RV is, then with the RV in the circuit, this is the voltage that you're getting, and without the RV in the circuit, this was the voltage. So you can calculate how much error you're getting as a result of RV being in the circuit. Now, to minimize that, you can simply say RV has to be infinity, which is obviously not possible. But the other thing that you could say is that as long as RV is much larger than R2, then the measurement is accurate. Because when R2 is in parallel with RV, the result of the two would be R2 RV over R2 plus RV, right? If RV is much larger than R2, I can approximate this with R2. If given R2 is much larger than RV, right? I can approximate this with R2 RV over, ignore R2 at this point because RV is much larger than RV. So this would be, sorry, R2 much smaller than RV. So at this point, I can ignore R2 and this becomes R2 RV over RV. The two go away, and that's approximately R2, right? So the smaller, obviously the smaller R2 with respect to RV is, the more accurate my measurement would be, given that I can't have RV of infinity. So let's say RV is 10 mega ohm. Now measuring 1 ohm, 10 ohm, 100 ohm, I would imagine that would be relatively accurate. but once it gets to the mega ohm range, now R2 at that point is actually comparable to the value of RV. For example, let's say R2 is 1 meg. So if R2 is 1 meg and RV is 10 meg, the result of R2 in parallel with R meg is not going to be close to 1 meg anymore. It's actually about 10% off. And that means that the measurement would be about 10% off in terms of accuracy. So you have to be mindful of that when you're doing measurement. In other words, measuring small values of resistors given a known value of resistance for, or a constant value of resistance for the internal resistance of voltmeter are more accurate than measuring larger value of R2 when it comes to measuring the voltage. Okay, all that said, let's switch our attention now, start discussing measurement of the current. So I'm going to stop and then continue. Okay, so now we move on to measuring current, and for current measurement we have to break the loop open, the current loop open, and put my amp meter in series with the circuit so that the same current passes through the amp meter. So I'm going to open that up and put my amp meter here. Now the current is going to pass through my amp meter, right? This doesn't look good. So it goes through amp meter, comes back and continues. Good. So that said, it's obvious again that by putting the amp meter there, I'm changing the circuit. How do I change it? Well, obviously the amp meter, before the amp meter didn't exist, so the current wouldn't go through this extra device that we have here, so it's different. So how could I make sure that this, when I add this amp meter in the circuit, the circuit is as close as possible to what it was, or ideally the same as what it was before? Well, if amp meter is a short circuit, it's just a piece of wire, then I'm back to what it was before, right? So ideal amp meter is a short circuit, because it's in series with the rest of the components. If it's a short circuit, it's not changing the circuit, right? Obviously that's not the case. Internal to this there's a circuitry, but the closer to a short circuit that I am, the better. So let's assume that this is close to a short circuit, which means it's a small resistor, but consider that resistor. So the resistance of that, I'm going to call it RA, right? And now calculate the current. So before this was added, IS, which was equal to I1 and IS were the same, was equal to the total voltage divided by R1 plus R2. Now that I have added that, the current is going to be different, obviously. Well, you can go through that, but this is just too simple of a circuit, and we should be able to quickly calculate the new current. I'm going to call that the IA, the current that's passing through the ammeter, which is the current that we read. So IA is equal to Vs divided by R1 plus R2 plus RA. This is the resistance of the ammeter. So obviously this current is different than that current, and now you can see through these equations that making it a short circuit makes sense, because if you make it a short circuit, that resistor becomes 0, and this equation goes back to that equation. But if that's not the case, which is really never the case, you're dealing with an error. So the error is smaller when RA is a small, ideally 0. In other words, if I can ignore RA with respect to, or if value of RA is negligible compared to R1 and R2, then my measurement is accurate enough. Let's work again with the values. So if R1 is 1K, R2 is 2K, and RA is just 1 ohm, then these two numbers, 1,000, 2,000, so instead of 2,000, I'm dealing with 2,001. And most likely, that's not going to change the measurement, or my measurement is not going to be very sensitive to that. But if R1 is 1 ohm, and R2 is 2 ohm, and RA is 1 ohm, then the current is completely different when I add that resistance in, right? So in order to minimize the effect of the ammeter, I have to make sure that the resistance of the ammeter is actually negligible with respect to the resistors that are in this circuit, and therefore the current that is measured is not going to be much different than the current before you add the ammeter into the circuit. So again, for the voltmeter, the ideal situation is an open circuit, but it's never true. The best case scenario is to make sure that the resistance of the voltmeter is much larger compared to the resistors that exist in the rest of the resistors that exist in the circuit. With an ideal ammeter, on the other hand, you really want to have a short circuit, but since that's not the case, normally what you want to do is to make sure that the resistance of the ammeter is much smaller compared to the resistors that you're measuring, the resistors that exist in the circuit, so that the value of the current is not disturbed by the resistance of the ammeter that you add. With that, I'm going to stop this discussion and move on to the next lectures. Thank you. Bye.